How are you all doing today?
Doing well.
Cool deal.
Good.
So, sorry, go ahead.
I'm doing good, thank you.
So there's was potentially a little bit of confusion about the lecture material for today. What I had posted for yesterday covered both capacitors and inductors. So one video was covering the material for both yesterday's in-class meeting and today's. So with that being said, does anybody have any questions regarding any of the inductor problems that we worked yesterday or any of the material that covered capacitors that we're going to look at today? All right, nobody's saying much of anything, so give me just a second. All right, so we are going to work our in-class assignment first. And this first problem is another one where I typically get a fairly reasonable amount of questions on how to do it. So we're just going to talk about it a bit. So we have a specific value of a capacitor, and we are asked to determine the maximum amount of energy that can be stored by the capacitor if the voltage drop over the capacitor has that particular waveform. And then for the second part, that's one that's effectively much more straightforward than part A. So we want the maximum energy. So, and this shouldn't be a P, it should be a W for energy. So let me ask you guys a question. How do you think we should go about approaching this?
I did 1/2 times C times VC of T squared.
Okay, so the energy absorbed by the capacitor as a function of time will be 1/2 C VC squared. So there's nothing, I mean, that is absolutely the equation.
Yeah.
And we could approach this problem purely mathematically, and we get the correct result eventually. But
yeah, but you can see that the voltage is going to be 8 maximally because the maximum value of cosine is 1.
exactly right. So if we went through the math here, I'm not going to go through all of it, but I'm going to introduce a trig identity that would be useful. So cosine squared of x is equal to 1/2 cosine x plus, sorry, that's not right. Cosine x cosine y is equal to 1/2 cosine x minus y plus 1/2 cosine x plus y. If we applied that to our waveform that we have, we would have 1/2 C times 5 plus 3, and I'm saying cosine squared, so I'm going to call that cosine 200t times cosine 200t. That's the same as cosine squared 200t, right? I'm just spreading it out. We could apply this quantity squared. We'd have 1/2 C 5 plus 3/2 cosine 200t minus 200t, so cosine of 0 is 1, plus 3/2 cosine 400t.
We have to wind up combining terms and applying this trig identity again, and the math just gets incredibly ugly. We have our form 7 equal to 0 to find out stuff. Here.
Something's happening with your mic. I can't hear anything you're saying.
Yeah, we can't understand what you're saying.
So what I was trying to say was,
Hello?
Much better.
Okay, I had to mute and unmute myself. So what I was getting at was that using the mathematical method, following this math through, we would get just a really, really ugly looking function. We would have to take the derivative of that, and then we would have to set that derivative equal to 0 and then determine whether or not we're looking at a minimum value of the energy or a maximum value of the energy. So a purely mathematical approach to this problem will absolutely get you the correct answer eventually. But what the gentleman who was speaking earlier suggested of looking at it purely as the maximum value of the energy should correspond to a maximum value of the voltage makes perfect intuitive sense. So what he is suggesting is that WC max will be 1/2 of C VC max squared. So we need to determine the maximum value of this guy. Well, the maximum value of a cosine function is 1. And so the maximum value of a cosine squared is then 1 times 1 is 1. So we can see very easily that VC max is just 5 plus 3 times 1 squared is 8 volts, which is exactly what he suggested. And so we would have 1/2 times 0.2 millifarads times 8 volts squared is equal to 6.4 millijoules without bogging ourselves down in the math too much. So I want you guys to be able to critically think about the problems and not just try to brute force things with equations. So that's why I included kind of an awkward problem like that. All right, for part B, we are told that our current is 8e to the minus 100t milliamps for all t greater than 0. And we want to determine the voltage present as a function of time with the constraint that VC of 0 is 0 volts. So this is going to have us use our integral-based relationship, right? VC is 1 over C times the integral from some point in time where our voltage is known to some later point in time of the capacitor current as a function of what I'm going to call x, which is just a dummy variable, dx plus VC at T naught. Well, as VC at T naught is this exact expression here. We're told the capacitor voltage at time t is equal to 0 is equal to 0 volts. So if we substitute in our values, let's see, it was a 0.2 millifarad. So 1 over 0.2 millifarad times the integral from 0 to t of 8 e to the minus 100t milliamps dt, or dx. Plus 0 volts. We can factor out a common factor of 8 milliamps. So I'm going to play a little bit with the units here. So 0.2 millifarads. So that's 0.2 times 10 to the minus 3. So that's getting rid of my milli. And a farad is going to be an amp second per volt. I'm going to factor out 8 milliamps. So that's 8 times 10 to the minus 3 amps. Excuse me. When I integrate an exponential function, what do I need to do? So
The
e to the
e to the negative 100 will be the same, but it's going to be 1 over negative 100, like afterwards.
right.
Yeah.
So the integral of e to the alpha x is 1 over alpha e to the alpha x. So that means I'm going to pull down a 1 over negative 100, and the units here are per second, because this is a coefficient that is being multiplied by our dummy variable for time. So I can infer the units on that. If time is measured in seconds, then alpha needs to be in per seconds. And so we can see there that the amps cancel the amps, seconds multiplied by per seconds cancel each other out, and we are going to be left with e to the minus 100 x evaluated at t and 0, like so. So let's do a little bit of the math here. This 10 to the minus 3 is going to cancel this 10 to the minus 3. So we should have 1 times 8 divided by 0.2 times negative 100. We get negative 0.4 volts is our coefficient there. And this is going to be multiplied by e to the minus 100t minus 1. And I can get rid of this negative sign out in the front by distributing it, and that's going to give me 0.4 minus 0.4 e to the minus 100t volts, which I believe matches the answer here. Yeah, so I've expressed it in millivolts there and in full volts here, but it is the same answer. So just one thing that's going to trip a lot of students up is following the units on your homework problems and things like that. So be careful and don't be afraid to apply the fact that 1 farad is equal to 1 amp second per volt, and similarly 1 Henry is equal to 1 volt second per amp. These unit identities can be quite useful to make sure that everything's on the up and up. All right, let's look at problem 2. We have another graph problem here. We are given the current flowing through the 5 microfarad capacitor, and we also are given the initial condition that the voltage at t is equal to 0 is 0 volts. And for part A, we want to find the voltage drop across the capacitor at t is equal to 5 milliseconds. Part B asks us to find the power at t is equal to 3 milliseconds. And finally, part C asks us to determine the energy at t is equal to 1 millisecond. So let's look at part A. 5 milliseconds is right here. So my question for you guys is, what do I need to do? So we're given the current and we want to know the voltage. So which equation should we be looking at here as guidance?
The 1/c integral from t
Right.
naught to t.
All right, so VC of t is 1/c the integral from t naught to t of IC of x dx plus VC at t naught, where we're told that that guy is 0. So I'm just going to go ahead and put a big X through that. So 1/c multiplied by the integral. We're not going to bother doing integrals here because we have a graphical representation that's made of simply triangles and rectangles and good stuff like that. So I would argue that for part A, VC at 5 milliseconds is going to be 1/c, which was 5 microfarads, multiplied by the area of this triangle, the area of this rectangle, minus the area of that rectangle, because it's underneath the horizontal axis. Anybody have any issues with me breaking it up into 3 bite-sized pieces like that?
Not at all.
All right, so, and it terrifies me that I have to ask this, but I had one summer session to where I think 4 of my 11 students didn't know how to find the area of a right triangle. So could somebody tell me what the area of a right triangle is?
Base times height over 2.
1/2 the base times the height. So that's going to be a 1/2. The base here is this dimension. So the base has units of 2 milliseconds. And the height is this guy from here to here. So that would have 15 milliamps. And we have our rectangle bit right here. The area of a rectangle is simply base times height. So again, our base is 2 milliseconds. Our height is 15 milliamps. And finally, we will subtract this rectangle. And it has a base of 1 millisecond and a height of 5 milliamps. Technically, it has a height of -5 milliamps, but I've already taken care of that by this negative sign right here. So whichever way floats your boat, close that guy off, and let's throw this into our calculator. I got 8 volts exactly, which appears to match here. So did this process make sense to everybody? Because this is the alternative. Excuse me, in the graph problem that I had you guys look at last class, you had to be able to take the derivative of a graph by inspection, which is effectively simply being able to look at it and determine what the slope is. In a problem like this, you need to also be able to integrate graphically. which means you just need to break down the area in question into simple shapes, which you can easily determine the area of and then add them together. So either of these is fair game for your exam. All right, part B, we're looking at things at t is equal to 3 milliseconds. So that's this section right here. So we would have this triangle, which we already know how to take the area of, and this rectangle will give us our voltage, and then the voltage multiplied by our current at exactly 3 milliseconds will give us our power. So VC at 3 milliseconds, it's going to be 1 over 5 microfarads. We already know that triangle because we just did it. And now we're looking at this bit. So the base is 1 millisecond. The height is 15 milliamps. And so that gives me 6 volts. Our power is then VC at 3 milliseconds times IC at 3 milliseconds is 6 volts times 15 milliamps gives us 90 kilowatts. Easy enough. Any questions on part B? All right, so then you guys take a stab at part C. Tell me what I need to be doing.
Well, since it's asking for energy, we can just use that energy equation.
All right.
And then find the voltage at 1 millisecond, like we did in the previous problems.
Okay, so the voltage at 1 millisecond. So what am I going to do?
You're going to find the area under the curve at 1 millisecond.
All right, so I want the area of this triangle then.
Yes.
All right, so somebody other than you, because you seem to be answering most of the questions, tell me how I'm going to go about doing that.
It would be 1/2 times 1 millisecond times 7.5 milliamps.
Right. Yeah, nothing wild or crazy here. So 1/2 times 1 millisecond times 7.5 milliamps. We can figure out what the height of this triangle is just by inspection, because our slope is easy. I try to make that happen to where you can always just kind of look at it and do it. But there may be a case where it weren't that way. So for instance, if I instead had a waveform like this. So our triangle was of interest. Well, actually, that's based on what it looks like. It looks like it would be 10. Effectively, what I'm trying to get at is I could give you an odd time interval, and you would need to use the slope-intercept formula to figure out what the height is, which hopefully you all should be able to do at this point in your engineering careers. Slope-intercept formula being the, no, go away thing. Y equals mx plus b format. You can use that to find the height pretty easily. Okay, so this one didn't require that. So this voltage 5 times 1, 7.5, 10 to the minus 6. 0.75 volts by my calculation. So from this, let's see, 1.406 microjoules. All right, that seemed easy enough. Let's look at problem 3. Well, yeah, we'll do it. I was going to say, won't even bother. This should be pretty simple. But all right, for the capacitive network shown below, we're asked to determine the equivalent capacitance seen between the terminals when the switch is open and when the switch is closed. And it's got a little crossing section here that's going to make things arguably slightly more difficult. So I'm going to approach the problem by identifying my nodes. And let's see. I'll label them just for the sake of argument. A, B, C, D, E, and F. And I'll draw things out. A's way over here, B's way over here. So I have a couple of different paths that I can take. So for instance, I can go from A to B, I could go from A to C to D to B. So let's do that one first. So here's C and here's D. So from A to C, I have 11 microfarad. From C to D, I have a 5 microfarad. And from D to B, I have an 18 microfarad. So that takes care of this guy, and this guy. Then I can go from A to E to B. So from A to E is an 18 microfarad. And from E to B is a 15 microfarad. That takes care of this guy and this guy. And then my last path from A to B is A to F to B. Where from A to F, I have a 4. And from F to B, I have a 25. So this is going to be CAB is going to be 1 over 11 microfarads plus 1 over 5 plus 1 over 18 plus 1 over 18 plus 1 over 15 plus 1 over 4 plus 1 over 25. Where all of my capacitors that are in series, I'm adding like they were resistors in parallel, and then all of my parallel branches I'm adding together as if they were resistances in series. And I should get 14.516 microfarad. So my question to you guys now is, how is this circuit going to change when this switch closes?
Nodes E and F become one node.
Right, so I could modify my current drawing to this.
Pretty simple.
Yeah, and then we could approach this one. So this is open. Closed. So I'm going to take care of these bottom paths first. So the 18 and the 4 are in parallel. Right? So that means I'm going to have and the 15 and the 25 are in parallel. And then those two equivalent capacitances are in series. So that's why, so this is the series parallel combination part, this is the parallel combination part, and then this whole thing is putting them in series. Plus the capacitance of our top branch, which is 1 over 11 microfarad plus 1 over 5 plus 1 over 18 minus 1, which will give me 17.080. So combining capacitors is just the inverse of combining resistors and inductors. So nothing wild or crazy there. All right, so I want to look at, I think, one web work problem in particular. It's the wrong class. I believe it's on homework set 12. Probably. Yeah. Let me open up. All right, so this is homework 12. Problem. This is, in my opinion, probably the second or third most difficult homework problem that you're assigned for this entire class. In this problem, you are given a voltage source. Let me give myself more room. It's an 8 millifarad. This is a 24 millifarad. This is a 20 millihenry. This is Vs as a function of time. This current is Is as a function of time. And you are told that if Vs of t is equal to something, which I'm just going to put in my numbers here, 85e to the minus 77t millivolts. Actually, I should work it generically, so it'll be more helpful to everyone. So let's call it V naught e to the minus alpha t millivolts. And that Is at 0 has some particular value. Let's call this Is0. We want to find Is of t for t greater than 0. So we're given a fairly limited amount of information to solve for this time domain or time varying current. So does anybody have any thoughts about what I could do to make this problem a little bit more simple, or any idea on how to approach the problem? Either way is fine by me.
You can add the capacitors. Yeah, you can add the capacitors together. That'd probably be the simplest thing.
Yeah, so we can combine those two capacitances. Two capacitances in series can be combined into a single equivalent capacitance. So what's 8 millifarads in series with 24 millifarads going to be?
Six millifarads.
All right, so I'll erase this junk. I'll attempt to anyway. And we'll throw a 6 millifarad capacitor into the mix. Alrighty, so what that simplification does is it puts this voltage source, Vs of t, in parallel with that 6 millifarad capacitor and in parallel with that 20 millihenry inductance. So the same voltage drop is occurring over all three of our circuit elements. So whenever we have a single node pair circuit, like we do now, our best bet is usually to apply Kirchhoff's current law, because it's going to give us a good amount of information. So I am going to define a capacitor current, IC of t, down like so, and an inductor current, IL of t, down like so as well. Okay, everybody got any problem with that? The current's flowing into the positive polarity terminal. So we are working under the assumption that the capacitor and the inductor are absorbing the energy that's supplied by the source. Seems fairly reasonable to me. So what I'm going to do is I'm going to write the Kirchhoff's current law equation. And I can say that Is of t will be equal to IC of t plus IL of t. Does anybody have any problem with that? Alrighty, nobody's saying much of anything. The problem that I have here is now I have one equation with effectively 3 unknowns, but since all of our circuit elements are in parallel, I can express the current flowing through the capacitor in terms of our known voltage Vs of t, and I can express the current flowing through our inductor, at least partially, in terms of our known voltage Vs of t by using the relationships that have been developed for the last 2 lectures. So I could say that IC of t is simply C dVs of t by dt, and IL of t is 1 over L integral from t naught to t of Vs of x dx plus IL at t naught. So I would argue that if we had numbers right now, I could take care of this portion and I could take care of this portion. But what am I going to do about the initial condition on my inductor current? Any ideas?
Could we do current division with the IS at T naught?
So can we do current division with IS at T naught?
No.
Yeah. Right now, the only current division rules that we know of are strictly for DC,
Yeah.
and this is not a DC circuit.
Okay.
Sure, we will learn current division for steady state sinusoidal circuits, but this isn't one of those either.
Okay.
I'm going to posit a question for you guys. This Kirchhoff's current law equation is valid for all points in time. So shouldn't it be valid for a singular point in time as well?
Of course.
All right. So what I'm getting at here is that IS at 0 should be IC at 0 plus IL at 0. And we could rearrange this and say then that IL at 0 is IS at 0 minus IC at 0, which is IS at 0 minus C d Vs by dt evaluated at t is equal to 0. Can we do this math?
Yep, sure can.
Yeah, and so now we have all of the information that we would need to throw into this guy right here. The thing that I believe trips most students up on this particular problem is this guy, performing KCL at a specific time. It's not intuitively obvious that you should do that, but hopefully it's at least obvious that you can do that. If KCL is valid for all points in time, which it has to be because it is the law of conservation of charge in circuits form, then it needs to be valid for every instantaneous point in time as well. So I've given you the steps that you would need to take to solve this problem based on whatever your numbers are. Let me look and see if there's anything else that needs maybe some attention for this homework set. So let's see, the first problem, you're given a capacitor, and if V is this, then find I, blah, blah, blah. That's fairly straightforward. It's just applying the basic relationships, no analysis or anything necessary. Problem 2 is inductor combination and capacitor combination. That's easy. Problem 3, maybe. Yeah, let's look at problem 3. All right, so here's our circuit. We are told that if VC of t has some form, in this case, it's sinusoidal function, how can we find the S of t? So this is a single loop circuit, right? All of the elements are connected in series. So for a single loop circuit, how do we usually approach a problem?
KVL.
Yeah, KVL. So we would apply KVL where there would be some common current, I of t, flowing around this loop, right? So I'm going to call this guy VL of t, and we can write a Kirchhoff's voltage law equation that says that Vs of t is simply VL of t plus Vc of t, right?
Right.
How can I express VL of t and Vc of t in terms of my common current I of t?
VC is the 1/c integral, and VL is L d current equation over dt.
All right. So L dI plus 1/c integral from t naught to t of I of x dx plus Vc at t naught, which, yeah. Well, now let me think about this real quick. Yeah, no, that's perfectly reasonable. The question then becomes, how do we don't know what what that loop current is though, so how are we going to find that out?
Could we use that capacitance and that voltage to figure out that equation?
Right,
So
so
this gives us that equation.
yeah, so IC of t, which is going to be I of t, is simply C dV by dt, right?
Yeah.
Once we know that, we can plug that in up here, and then we're donezo.
Mm-hmm.
Another problem where you're just going to have to apply the rules for both the current voltage relationships for both capacitors and inductors, and then figure out how to get the information you're missing. So it's pretty similar, but in my mind, this one's a little bit easier. One thing that I don't know, that amuses me about these problems is that you guys don't even realize it, but we are solving differential equations here. So for some of you that haven't had some of your higher level math, this is probably pretty new, but we're going to be getting into even more differential equations in the coming lectures. Only first order, so nothing crazy wild. But yeah, so like this is an integral differential equation that we're actually having to solve using our circuit analysis techniques. So you're getting
Cool.
high level math here. So yeah, what was your question or comment?
No, I said that it's pretty cool that we're solving those, and I mean, I'm not in differential equations yet.
Yep. Yeah, we're gonna be going through. So in your Math 245 class, you're gonna learn a lot about solving differential equations, starting with what I believe are called homogeneous differential equations. Just means you're setting things equal to 0. And then you're going to be working on heterogeneous differential equations where the differential equation is set to some numerical value or a function. So what we've got right here technically would be a heterogeneous integral differential equation because it contains both a derivative and an integral, and we're able to solve it just using circuit analysis without having oodles and oodles of mathematical practice. So yeah, we're using calculus to do some very, very interesting things that are, like I said, likely beyond what you've actually learned in your math classes yet. Because circuits behave in a very particular and specific way. There are very well established rules, and if we know how to apply those rules, we can solve anything. So unless anybody has any questions on anything, that's enough ranting out of me for today on the math that we're doing. So I guess we can wrap this up unless anybody has anything to ask a question about or talk about. Alrighty, well, I'll see you guys on Thursday, and I will endeavor to get both this lecture and or this Zoom meeting and yesterday's Zoom meeting up on YouTube and Google this afternoon, so you can use it as you see fit. All right, catch you guys later.